Let's take some notes on 4-5 graphs of tangent, cotangent, secant, and cosecant. Of course, we're going to start with tangent, and hopefully you remember that tangent is a ratio of sine and cosine. Tangent is really equal to sine over cosine. So let's consider what knowing this might tell us for the graph of tangent. Think about it as a fraction, right? If the numerator of our fraction is 0, if sine of theta, oh, sorry, I guess I used x. I'll use x. If sine is 0, then tangent will be equal to 0, because that's how a fraction works. What else do we know? If the denominator of a fraction is 0, then that thing will be undefined. So if cosine is equal to 0, then tangent will be undefined. We'll talk about what that means in a moment. What else? If sine and cosine are the same thing, if sine is equal to cosine, then tangent will be equal to 1. So these are the main three things we can kind of know based on just the graph, or excuse me, not the graph, the equation of tangent. Let's consider how these might play out with our function. So in order to know what is going to happen here, I am going to sketch tiny little sine and cosine graphs, just kind of briefly. We know that both sine and cosine have a period of 2 pi, and they are cut into 4 equal chunks, pi over 2 and 3 pi over 2. Sine starts at the origin, goes up to the middle, down and back to the middle, right? Here is sine. And cosine, we know, starts at 1, goes to the middle, down to -1, back up. And so here is the graph of cosine. And of course, we know they go on forever and ever in both directions, but for now, these are kind of enough. So let's start. Tangent will be 0 at the places that sine is equal to 0. So right now, that would be at these 3 points. So at 0, at pi, at 2 pi, and of course there are more places, but we're just going to consider these. Tangent will be undefined, meaning it will have an asymptote, because to be undefined means you can't exist. And so this graph will actually have a bunch of asymptotes, specifically at the places where cosine is equal to 0. So that would be here and here at pi over 2 and 3 pi over 2. Again, there are more than just those two, but we'll start there. We also know that tangent will be equal to 1 at the places where sine and cosine are the same. So notice they're the same right there. They are also the same right here. And so where is that? Well, if we consider it's halfway between 0 and pi over 2, this would be pi over 4. So this is 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, which is just pi, right? And then finally we get 5 pi over 4. So the places that sine and cosine are the same are pi over 4 and 5 pi over 4. We could also consider the unit circle for this, right? The places where sine and cosine are the same are, I'll draw a really quick unit circle, are at 45 degrees, where it's the square root of 2 over 2, square root of 2 over 2. So we've got a lot of really good information here to help us draw our graph of tangent. I dragged the information in from the last page, and we are going to start by sketching an XY coordinate plane. Oops. And I don't really know a ton yet, but I know that I'm going to scale my x-axis in terms of radians. And so if I look at all of the radians I have here, I see that the smallest is pi over 4. So maybe it's a good idea to start doing this in terms of pi over 4. 1/4, 2/4, pi over 4, so that would really be pi over 2. 3/4, 3 pi over 4, and 4/4, which would be pi. 5 pi over 4, 6 pi over 4, which is really 3 pi over 2, 7 pi over 4, and then 8 pi over 4, which is 2 pi. I'm also going to take a moment and put that same scaling on my negative x-axis. I'm going to just do to negative pi, I think. That'll kind of give us enough. And then let's start with our asymptotes. Let's sketch in our asymptotes. So I know there's an asymptote at pi over 2, so that's right here. And I know that there is an asymptote at 3 pi over 2. Now, I notice that the distance between pi over 2 and 3 pi over 2, that this distance is pi. And it's a pretty good guess then that each asymptote is going to be pi distance away, because just like sine and cosine, tangent repeats itself. Now, if I want to be totally sure, I could go back and look at my graphs of sine and cosine for a second and maybe keep sketching cosine, right? Because that's where tangent will be undefined. So if I continue cosine for a second, the places where cosine is 0, notice, is going to be at negative pi over 2, and then negative 3 pi over 2. So I can be fairly confident, and I am correct, to say that there is an asymptote at negative pi over 2, and then every other iteration of pi. Okay, so we got our asymptotes drawn. Now let's draw these points that we know. Tangent will be equal to 0 when sine is equal to 0, which means at 0, at pi, at 2 pi, at negative pi, etc. And then we know tangent is going to be equal to 1 at pi over 4. So I didn't do an x-axis here. Let's say this is 1 and negative 1. And then we got a point at pi over 4, 1. We've got a point at 5 pi over 4, 1. And technically, this is kind of enough to see the graph of tangent, but only to a well-trained eye. Let's just think for one more moment at what's going to happen at, let's say, 3 pi over 4. Well, I know on my unit circle, this point right here is negative square root of 2 over 2, positive square root of 2 over 2. And so that means my ratio of sine over cosine, sine is y, cosine is x, will be square root of 2 over 2 divided by negative square root of 2 over 2, or a negative 1, which means at 3 pi over 4, this graph is at negative 1. Now, technically, this is enough to see what tangent looks like because it's this kind of really elongated curve that goes on forever and ever in both directions. I can notice the pattern, so I see because I am at pi and then 1 to the left and I'm down here, well, here at 0, 1 to the left and down would be negative pi over 4, comma 1. So we've got that curve. Sorry, that was not very smooth. And I can keep drawing in my curves for, oh gosh, that was terrible, tangent. And here, my friends, is the graph of tangent. I love it. It's beautiful. Now that we know about the graph of tangent, what can we figure out about the graph of cotangent? Well, let's think. Cotangent of theta is equal to the reciprocal of tangent, 1 over tangent. Or another way we could think of that is cosine over sine. So a lot of the things that we were considering before are going to be true. If sine, oh goodness, if sine is 0 in this case, if sine is 0, then cotangent, oh my gosh, I need to learn how to write. Cotangent will be undefined. If cosine here is 0, then cotangent will be equal to 0. And again, if sine is equal to cosine, cotangent will be equal to 1. So let's consider how this is going to look. If you want to pause the video right now and get in your axes, the exact same as tangent, that would be great because I'm going to pause mine, draw that, and then jump back in. All right, I have my axes here. Let's think. We know that this function will have asymptotes where sine is equal to 0. Sine goes through the origin. Oops. So we are going to have an asymptote here. Sine also hits the x-axis at pi and at 2 pi, at negative pi, and at negative 2 pi, which isn't on here. We see a couple things that we can notice now because cotangent is going to look really similar to tangent. One thing we can pay attention to is the distance between each of these asymptotes. Notice that there's 1, 2, 3, 4 equal pieces. So pi over 2 is in the center. If we think cotangent is going to look like tangent, I can make an educated guess that maybe there's a similar point in the center, just like tangent had. And if I look right here, cotangent will be 0, where cosine is equal to 0. Well, then I know, yes, I'm correct. There's a point at pi over 2. There's a point at 3 pi over 2. There's a point at negative pi over 2, and other places to the left and to the right. And then where sine and cosine are the same, cotangent will be 1, which means at pi over 4, it will be 1. At 5 pi over 4, it will be 1. At negative 3 pi over 4, my function will be 1. And at 3 pi over 4, 7 pi over 4, those are going to be the places where sine and cosine are the same value, but different signs, S-I-G-N. So that would be where cotangent is negative 1. And we notice that we're seeing a very similar graph. It's just falling instead of rising. And this, my friends, is the graph of cotangent. Absolutely beautiful as well. Let's talk secant. So secant, if you remember, is the reciprocal of cosine, 1 over cosine. So things we can notice, if cosine is equal to 0, then secant will be undefined. And if cosine is equal to 1, then secant will be equal to 1. We're going to actually start by just drawing the graph of cosine. So I know that I need to get to 2 pi, and then I'm going to cut that in half to be pi, half again, pi over 2, and 3 pi over 2. And then I'm going to do the negative side, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. And then again, I'm going to draw in cosine. Oops, I forgot my y-axis. 1, negative 1. Okay, now I'm going to draw in cosine. Up to top at 1, to the middle, down, back to the middle, and up. And then I keep that motion over to the left here. I'm going to sketch in my cosine graph. And then I'm going to make it really light. Now, you can't do that necessarily with your pencil, but I think you'll get the general effect here. Why am I making it really light? Well, because I'm not drawing cosine. I really want to draw secant. So let's look at a couple things. Secant will be undefined. We'll have asymptotes where cosine is equal to 0. So secant's going to have an asymptote here. It will have an asymptote there. At negative pi over 2, positive pi over 2. And I notice that cosine, where cosine is 1, secant will be 1. So we'll have these same points, and it will also have the negative points as well. Then let's think about this. What else will this function have? Well, if this is a y value of 1, I know 1/2 is somewhere here, specifically right about there. Cosine of whatever that value is, let's just say theta, is equal to 1/2. The reciprocal of 1/2 is 2. So that means secant of that same value will be equal to 2, or I know that at this x value, my y value will not be 1/2, but it'll be up here at 2. That same idea is true, and if you kind of see what's happening, Over here, it's the exact same idea. This negative x value will give me a y value of 1/2. That negative x value, when I take the reciprocal, will give me this 2 up here, and I've got this parabola looking thing. And, surprise, it does this at every maximum and minimum. So it's got these parabolas opening up and down in each of these little quadrants. Oops, that's supposed to be secant. The curves are secant. This purple thing, that's cosine. Remember, we don't actually want that with the secant curve. We just drew it kind of to help us out. And then last but not least, cosecant. Cosecant is the reciprocal of sine. So hopefully if you paid attention last time, we're really going to be doing the exact same thing. I'm going to pause this video and sketch in my x and y axes here. You should do the same. Got my x and y axes. I'm going to draw sine. I know it goes through the origin, up to 1, back to the x-axis, down to -1, and back up. And then it moves in the same wave form on the other side. I'm going to sketch in sine, but we're going to kind of make it really light because, again, we're not actually drawing sine here. We are drawing cosecant. So I'm going to take this and I'm going to make it a little transparent. Same pattern as before. The places where sine here is 0 are going to be the places where cosecant, oops, I did not mean to change the color. The places where sine is equal to 0 are the places where cosecant will have asymptotes. So cosecant will have an asymptote at pi, at 2 pi, at 0, negative pi, negative 2 pi. And then we're going to have those same parabolas that we saw from before. I'm not going to go through these steps here because it's honestly the exact same idea. It's just sine instead of cosine. And remember, we mentioned that sine and cosine are horizontal shifts of one another. So hopefully it makes sense that secant and cosecant would also be horizontal shifts of one another. All right, sorry that was a little longer. We had a lot of graphs to get through. Have a good day.